Okay, so today we're going to take a look at charging systems and control circuits. So how an alternator is driven depends on the application. Most alternators are driven by either a V-belt or a serpentine belt. So when we're troubleshooting any type of charging system problem, again, we want to look at some of the very basics in the system. Are the belts there? Are the wires broken? But for us, we got to understand how the internal components work in order to diagnose a charging system properly. So our charging system consists of our batteries, and from our battery we have our cables that run to our starter. Then we also have a smaller cable that runs from our starter positive to our alternator. Now, we've discussed this before, is making sure that our ground circuit is working properly, because without a ground circuit the alternator just won't work properly. So when we're doing voltage drops, we also have to do the voltage drop on the ground side. Now the rest of the circuit is our starting circuit, which we're going to be discussing at a later date. Okay, now again, one of the things we have to make sure that we're using the right battery for the application of the machine that we're looking at. If the battery capacity is too small, that means that the alternator is going to run continuously to keep charging that vehicle. Again, first thing we want to check is the battery. Is the battery working properly? And how we do that is we load test it. Now, when we're taking a look at the alternator and how they're set up, the newer ones that use a serpentine belt also use a belt tensioner. And making sure that the belt tensioner is working properly. So here we have a belt tensioner, and all it is a pulley that runs on a bearing. Now this has a spring inside that keeps a proper amount of tension on that belt at all times. So some of the problems that we run into is, oh, I can't get exactly the same length of belt. So if I get a belt that's too long or a belt that's too short, we're going to end up with problems, because as an alternator starts to charge, it creates a magnetic field. That magnetic field will slow down an engine. So if the belt is too long, the alternator could slip. If the belt is too short, it could put too much load on the front bearing of the alternator, and we could end up with a bearing failure. So it's really important to make sure that when we are installing a new belt, that the belt is exactly the right length for that application. When we're taking a look at the components of an alternator, one of the things that we have is we have regulators. They're internal regulators built inside the alternator. Now this on a Lease in the Ville, this internal voltage regulator, we can take it out. When we get into the Delco Remis, we can't. They are an integral part. We have to really take the whole alternator apart to get at the voltage regulator. On the older vehicles, they used to have an external voltage regulator that was mounted on the firewall. Now, before they came out with electronic voltage regulators, they used to use 3 separate coils inside this box to control the field. Now when we look at alternators and how the circuits are set up, we're going to take a look at the alternator as 2 separate circuits and understanding how each of these circuits work to charge a battery. So what we have here is, off of our battery we have our key switch. Once we close our key switch, it sends power to our external voltage regulator, and from there it goes to the F terminal on the alternator. The F terminal is the field terminal, and that is what's going to build the magnetic field internally inside the alternator. Now if you remember back from when we were discussing basic electrical, if we take a wire or a conductor and move it through a magnetic field, we're going to induce voltage. Now when we move it back out the other way, it's going to induce voltage in the opposite direction. And this is called AC voltage. And this is what happens when we have an alternator. It produces AC voltage. Now AC voltage for us doesn't do any good. We have to convert that AC voltage into DC voltage to be able to charge a battery. With AC, it pushes and then it'll pull. So we have what's called an AC sine wave when an alternator is producing current. So again, what we have on an alternator compared to a generator, in an alternator we have our magnetic field in the center, and that is the rotor. So off of our battery, we go into 2 slip rings and 2 brushes. So as power is fed into the rotor, it builds a huge magnetic field. Now this magnetic field, again, if you remember back from basic electrical, a magnet has flux lines that run from the north to the south pole. Now, as this rotor is spinning and those flux lines cross a conductor, it induces voltage within that conductor. So anytime it's in line with that conductor, it's inducing voltage in that conductor as it's moving through there. The same with the south pole. So we have current flowing in one direction, it'll light up a light bulb. Now as we go 90 degrees to that conductor, no voltage is induced in that conductor and the light bulb will go out. But then when we get back down to the other side, voltage is going to be induced in the opposite direction. And here's we have it here. We start at 0 degrees where it's not in line with the conductor. As it gets close to the conductor, it induces the maximum amount of voltage. As it comes out of alignment with that conductor, we get back to 0 volts. When it starts to rotate in the other half, we have voltage in the opposite direction. And then it goes back up to 0 when it's not in line with the conductor. Again, this is AC voltage, which doesn't do us any good. So what we want to be able to do is we want to be able to change that AC voltage into a DC voltage so that we can use it to charge our battery. So some of the things that we see inside an alternator, and it's important to understand how these work. We have a heat sink. So in the back of the alternator we have rectifier diodes. So we have what's called a rectifier bridge. There's 3 negative and 3 positive diodes. Now every time one of these diodes switches, it generates a little bit of heat. So we have to put these diodes into a heat sink to get rid of that heat or the diode's going to burn up. The other thing we have is a fan on the front of the alternator. So the fan pulls the air through the back of the alternator and out the front, because we want the coolest air to cool those diodes. That's what we're after, is to take that heat away from those diodes so they don't burn up. Now this fan is a directional fan. You can get different types of fans. It doesn't matter which rotation it is, but if we put the wrong fan in, what we're going to be doing is bringing air from the front through to the back. So one of the common failures is a truck that's leaking a little bit of oil. That oil collects with dirt and plugs up the back of the alternator. Now if we don't have any airflow through the back of the alternator to cool those the heat sinks, we're going to overheat the diodes, we're going to have an alternator failure. So it's one of the visual checks we can do as we're taking a look for problems of what's happening. Now, the other thing that we have inside, and this is the rotor, this is the component that builds the huge magnetic field we need for inducing voltage into the stator. And all it is a coil of wire with 2 pole pieces. So what we'll have is we'll have a north, a south, a north, a south, a north, a south, all the way around. Also on there we have our 2 slip rings, because we have to be able to feed power or current through that rotor to induce that magnetic field. Otherwise, if no magnetic field, no charging. So when they're all put together, this is what we have if we take a look at the rotor. So this is our setup. This is what our rotor looks like. So we'll have a north pole, south pole, north pole, south pole. And as this rotor is spinning, we have flux lines that come off that go from the north to the south. As these flux lines cross a conductor, it'll induce voltage in that conductor. So if we have our stator, and we have all these windings in our stator, as these flux lines are crossing a conductor in the center here, it's going to induce voltage in that conductor and send it out through these three leads. So, again, we have our slip rings, and our two brushes are going to fit on the slip rings. We have a back bearing and a front bearing. Now the front bearing is a bigger bearing and it carries the most amount of load. Again, it's really important that if we're adjusting belts, if we have V-belts, we have to adjust them. We don't adjust them too tight, or we're going to put extra load on that bearing. So this is how our field circuit's set up. So off of our ground from our battery, goes through our field circuit. If our field circuit is open, no current can flow through the rotor and it can't produce a magnetic field, and again, it's not going to charge. As soon as we close the contact here, current is going to go through our slip rings, through our rotor, out the other slip ring, and back to ground to complete our circuit, and we're going to build a magnetic field. Now, we have to be able to go in and we have to be able to control how big our magnetic field is going to be. And we're going to do that with a voltage regulator, which we'll discuss a little bit later. Now, these are two different types of alternators. This is probably one that we see most common. It runs on a V-belt, or it could be a serpentine belt. The other type of coupling is going to be a direct drive. So this could be bolted directly to the engine, so there will be no slippage in this one at all. Now we take a look at our stator, and again, a stator, this is a three-phase stator, which means we have three separate sets of windings. So they're laminated and they have a resin coating on them so that they don't contact each other, otherwise we're going to end up with a short. Remember, the three faults that we have in the circuit is opens, grounds, and shorts. And so if this thing gets too hot, the coating on this varnish is going to bake off and start to fall apart, and then we're going to have wire-to-wire contact, and we're going to end up with a problem with our alternator. Now when we take a look at the phases, and again, if we take a look at what we were taking a look at earlier with a single wire, which is single phase, but we have three phases. So a single phase would look like this. When we get into three-phase, we have three separate phases that induce voltage into, or current into that stator winding. Now, if they could color code them, again, we need as many wires as possible. The more wires we have in each of the phases, the more voltage that is induced in that winding as the rotor spins and those flux lines cross that wire or that conductor. It's going to induce more voltage. So two different types of windings that we're going to see. We're going to see a Y-type stator, and how we have to take this apart to identify it. What we'll see is we'll see three separate ring terminals with a single wire on each. And then what we'll do is we'll see another set that all three wires are wrapped together, and that's the center point. Now, there are certain applications where we might want a Y-type stator, so a Y-type alternator, or a delta style. And if you take a look at this one here, we have three ring terminals, but we have two wires on each. And this is a delta style. So if you take a look at these and you separate them, you can take a look and you can see the two wires on each. So when we go into a single cycle, which means that this is going to turn twice. Now what happens is we end up with this AC sine wave, and again, this AC sine wave doesn't do us any good for charging a battery. Now how we can fix that. So in a single phase, if I put a diode in, now forward biasing means that I can have current flowing through a diode. We've already discussed how a diode works. So as the North Pole passes by a stator winding, it's going to induce voltage. That voltage is able to get through the diode, out through my load. Let's just say my load is my battery. It can go out to the battery from the negative side of the battery. Again, it goes back to that stator winding. Again, we need to have a complete circuit in order for current to flow in this. Now, what happens when the South Pole gets close to the stator winding? Well, as it induces voltage, no current can flow because it can't get past that diode. So this is what's called half-wave rectification. We're able to use this one wave, okay, the upper half, but the lower half is no good to us. So we want to be able to use this other half. So this is what the sine wave would look like. So the lower half that is supposed to be here is gone because the diode prevents current flow. So how do we fix it? Well, if we just have a single phase again, by putting 4 diodes in, we can now rectify that bottom and control it and use it to charge. So as power flows out, it can go through here. It can't get through here because it's blocked by this diode, so it can go out here. It can't go in here because it's blocked by the diode, so it has to go out to my load. And again, we have to have a complete circuit. So from the battery, it goes back in, goes in here. Now it can't get out this one because the voltage here is pushing that diode, so it won't go. So it has to go this way to complete my circuit. Now if we take a look at the other half, now current flows, it's built up in this way here. Again, it can't get out there, so it's got to go out here. Can't get out there. It's got to go out through my load, back in, through to complete my circuit. So this will give me full wave rectification by using 4 diodes in the system. Now this is a single phase. So what we see is 3 phase, so we're going to have to use more diodes to control this. Okay, so now if we take a look at our heat sinks. So in our heat sink we have 6 diodes, 3 negative diodes and 3 positive diodes, and how they're set up depends on whether we have a negative ground alternator or a positive ground alternator. So for the most part we're going to deal with negative ground systems. So if that's the case, then our negative diodes are grounded to the case and our positive diodes are insulated from the case. And if we take our stator is going to hook up to one on each of these. So each phase is going to hook up to a set of diodes. You can't see the diodes here, but there's this copper strap that's here and here and here. So there's one diode pressed in here and one diode pressed in here. So again, if we have a negative ground alternator, we're going to have our negative ground diodes pressed into here and our positive diodes pressed into there. So how does this all work together? Well, inside our alternator, inside our case, our rotor is going to spin. Our stator is stationary, it just sits there, it doesn't move. But as this rotor spins and our North Pole and our South Pole pass one of the conductors in here, it's going to induce that voltage. The other thing we have to pay attention to if we're rebuilding alternators is these insulated screws. Now again, if we take a look at our rectifier bridge, our negative heat sink is grounded, but our positive heat sink is insulated. And if I don't put one of these insulating screws on my positive, what's going to happen is it's going to short out the positive side and it's going to blow the diode, and then we're not going to get charging on it. So if you take a look internally inside an alternator, this is where our heat sink is. Okay, so our negative heat sink is at the very top, and these screws here and here are not insulated. They don't need to be because they ground that. That's the negative side. But if you go to the positive side, they've got the plastic inserts on them. And then off of this here, it goes up to our voltage regulator. Also on the back, we want to have insulating washers. And there again, if you take a look at the back side of this, this is our positive stud, this is our R terminal, and this is our I terminal. Now we want those insulated. The other thing you're going to notice on the back is we also have a stud that we can use for a ground. Now again, if we don't have a complete circuit, that alternator is not going to charge. So it could be as simple as putting a new ground strap on an alternator to get it to charge. The other thing we might see internally or externally is a capacitor. Now the capacitor is going to take any voltage spikes out and make them nice and level so that we get clean voltage. And all a capacitor is 2 layers of tin foil with a dielectric material that keeps them separated. So as we get a voltage spike, it's like an electrical accumulator. As we get a voltage spike, it will go into this dielectric, or into the tin foil, and go around, but because there's no ground to it, it just sits there. Now when there's a low part, then what's going to happen is now that's going to come back out and keep that voltage nice and level. So if we take a look at how this is an alternator, we have our 3 negative diodes and our 3 positive diodes. We have our 3-phase power in a Y-type stator. So what these 3 diodes do is they're going to control all 3 phases so that we can charge a vehicle. Now, the other thing is, if we take a look up here, this is our rotor field. Now again, like I said earlier, we're going to separate this into 2 separate components. One will be our rotor, and the other will be our stator and our diodes. So how does it work? Well, as the rotor's inducing voltage in one of the stator windings, it can go out any one of those 3 diodes depending on which ones are being induced. So it can go that way, it can go that way, or it can go this way or this way. So there's a lot of different ways it can go, but it can only get out one set of diodes at any time. So what's happening here is now what we're getting full wave rectification in 3 phases. And this is what we need to be able to charge our battery. So out of our stator, we're getting AC current. But once they get past these diodes, we've now converted that AC into DC. Now that voltage can go out and it can charge our battery. So taking a look at how a delta style is compared to a Y, again, it can go through any one of these to get out our diodes to charge our battery. And again, remember, we also have to have the ground side of the circuit. Because if the ground is missing, we don't have a complete circuit, we're not going to charge. And this is, if we put this on an oscilloscope, this is what we would see. Okay, so this is a picture of our negative or positive diodes, but we also have another thing in some alternators called a diode trio. Diode trio has one purpose in life, and that's it. And it's to convert AC. So you can see we have a tap that runs from our stator. So this stator, each one of these is hooked to the rectifier bridge. So our diode trio takes AC power, and through these 3 diodes, and again these 3 diodes are insulated from ground, they're positive diodes, We convert AC into DC power, but its one purpose in life is to feed the rotor. That's it. It doesn't do anything else. So, again, depending on where our voltage regulator is in our system, it's going to control how big that field circuit is. So when I first start a vehicle up, say I've had my lights on, this voltage regulator is going to sense the battery voltage is low, and it's going to basically put that rotor into what's called a full field. So the magnetic field is going to be massive. So the bigger the magnetic field as the rotor's turning, the more current it's going to produce. Now, as that vehicle runs for a couple of minutes, it starts to charge the battery up. Now the battery's going to give pushback to the voltage regulator. As it gives pushback to the voltage regulator senses that the battery's coming up to charge. It's going to shrink that field till it's smaller and smaller. And once it's up to full charge, then it will be next to no field. Now, if we turn any components on, we're going to create a demand on the circuit, and the field would start to get bigger. When we take a look at, we're going to take a look at the voltage regulator and how it does that a little bit later. Now, how do we know what type of alternator are we dealing with? Is it negative ground, is it positive ground, is it 12 volt, or is it 24 volt? Well, on the alternator, there's either a tag or it's stamped. On this alternator here, this one is 12 volt N for negative ground, and it's a 150 amp alternator. So this is where, when we're going to test an alternator, we need to know what the amperage output is. When we're changing an alternator, we need to know whether it's a 12 or 24 volt, whether it's a negative ground or a positive ground. Because if I put a positive ground alternator on a negative ground system, my diodes are backwards, it's going to go poof. So it's not going to work. So making sure that we install it properly. When we take a look at the brush and spring assembly, okay, so this is where the rotor gets fed. So from our power, it goes in through one of the brushes, through our rotor winding, out the other brush, and again it could go to the voltage regulator, it could go to ground depending on the style we have. When these brushes are 50%, they're considered to be worn out and should be replaced. Now the other thing we see is a brushless alternator. So they don't use brushes. So what they have is they have this setup, and really all that is the rotor. Okay, and it's stationary. So we have two wires that feed this. Again, it works the same way. But what we have is we have this hollow rotor, and it spins around. Now this is building up my magnetic field, so it does exactly the same. We'll have a north pole, a south pole, north pole, south pole, all the way around, so we can still build a magnetic field that's rotating, that's going to cross those conductors to induce voltage. So this is, when I said we break it up into two separate circuits, this is one of the circuits. So this circuit contains our field windings, our slip rings, our brushes, and our voltage regulator. Now there's two different styles that we're going to take a look at. This is an A style voltage regulator, which means that power comes in from my battery, in through my rotor windings, out the brush, through the voltage regulator to ground. So in an A style, the voltage regulator is after the rotor windings, and it controls the ground side of the circuit. The second one is a B style, and B is before the rotor winding and is controlling the power side. So when we close the key switch, voltage will go through here, through my rotor windings and out to ground to complete the circuit. So always remember, A is after, so it controls the ground side. B is before, and it controls the power side. So if we take a look at our rear housing. So again, this is a bare housing, doesn't have anything on it. These are our insulated connectors here. And back in here, where these openings are, is where my rectifier bridge and my heat sinks are going to be cooled. The other thing on the back of an alternator you'll notice is the little shape of a D. And most alternators will have it. On here, it's right here. Now, what that D is for, and if you take a look internally, and I don't think you can see it here, I'll get a picture of it later. But inside here, there's a little steel tab. And what that's doing is, if you stick a screwdriver in there and go up, there's a little tab you'll touch. And what that will do is that will full field the alternator. It will tell the alternator, basically, if you go back to a circuit, let's just take a look at it. If we go back to this circuit here, oops, this circuit here, when I put the screwdriver up, what it's doing is we're attaching that directly to ground. And when we do that, we take the voltage regulator out of the circuit. So what it does then is, now we're getting full power to the field. The field's going to be as big as it can possibly get, so we're going to get a large amount of output. So be very careful when you're doing that you don't do it for a long period of time, because it can exceed what the battery's capacity is, and we can fry some electronics. So be very careful when you're full fielding for any reason. Okay, now, depending on, again, on the application, we might find that an alternator, it can't survive in the dusty conditions, so it may be air-cooled. So it's completely sealed, and it's air flowing over top of the alternator that's going to keep it cool. There are also some that are oil-cooled. So they're hooked up to the oil system, and oil flushes through the alternator, and that is what keeps the alternator cool. And then that oil just drains back into the sump. So when we take a look at voltage regulators, this is on a Elise Novell and this is on a Delco Remy. So this is what's controlling it. So these are electronics. So that's one of the things is, if we take a look at electronics, they make a square wave. And if we remember what a square wave looks like, we have on time and off time. So if the alternator senses that the battery is close to being dead, then what we're going to do is we're going to have a large amount of on time and a very small amount of off time. But once the battery comes up to capacity, we're going to see the opposite. We'll see a very small on time and a very long off time. So the magnetic field is smaller, so we're not producing the amount of current that we need. Okay. So on the back of the alternator, there's also an R terminal. Now, if you take a look at where the R terminal is set up, it's set up and it goes into one of the stators. Now, and I've had this happen once where one of the guys put an alternator on a vehicle and it wouldn't charge. So he come to me and he said, well, I just put the brand new alternator on there and it won't charge. So what you have to do is you have to do what's called flash the alternator. What you're going to do is you're going to take a jumper wire and touch these two together just briefly. And what that'll do is it'll show the alternator, the way current is supposed to flow. The other thing we have to be aware of, and I've seen this happen, is when we're changing the pulley on these, is the new ones now don't have a key cut in them. So the pulley can actually slide on here. Now on the end of this is set up to use an Allen wrench and a wrench. Most people, what do? Well, they put their impact on there. But I've seen an impact just from the vibration break the brushes on the slip rings, and now your alternator is no good. So be very careful when you're changing pulleys. Make sure you don't use something that's going to break the brushes. Okay, so this is simple and easy. Again, you just take it from the power wire, flash it to the R terminal, and it'll set up the power flow. Now, this is a picture of a voltage regulator. So we talked a little bit about diodes. So we have a diode here. This is our diode trio. And again, our diode trio's purpose in life is to change AC to DC for the voltage regulator, and that's it. So this is our number 1, 2 terminal. So if you take a look at the back of the alternator again, so this is our 1, 2 terminal up on top. So what happens in here is this is controlling how big my field circuit's going to be. Now, some of the things we didn't talk about, we've talked about resistors. We didn't talk about transistors and what a transistor does. Well, a transistor is really 2 diodes and how they're set up. So there's NPN and PNP. So how an NPN is set up is, if we take a look at, for instance, a very simple diode. So if we have a diode, we have an N and a P, negative, positive. Well, a transistor, it can have another P here. Now, how this works is if we have a PNP transistor, it needs a ground circuit to activate it. But if we have an NPN, it needs voltage to trip it, to tell it to open up. And all a transistor is a very, very, very small relay. Okay, so it's how we control it. So I can control the power side of a relay, or I can control the ground side of a relay however I want. And that's all this is doing in the circuit. So what happens in here is voltage that's produced from our diode trio comes in through here. It can't get out through that diode, so it can't go anywhere. But what happens is now voltage can come around here, can go through here, up through here. It can go back here, but again, we already got 12 volts of push there, so nothing's going to happen. So it has to go through here, but in order for this to be tripped open, power has to come through here. I'm not going to ask you to explain how a voltage regulator works. Just understand that it is a square wave. So this is how voltage goes through here, okay? So once this is tripped and triggered open, or sorry, closed, it can get through ground and we're going to have a complete circuit and it's going to charge. Now we also have another thing that we haven't talked about. It's called a Zener diode. It's like a normal diode, but it has a breakdown voltage that will allow reverse biasing once voltage reaches a certain point. Now, for an alternator 12 volt, that breakdown voltage is roughly 14.2 to 14.5 volts. So once the battery pushback gets to that point, that Zener diode is going to open and it's going to shut this circuit off so it can't charge anymore. Now, we also talked about how do we know if an alternator is charging? Well, there's 3 different ways. We can have an amp meter, and an amp meter is hooked in series within the circuit. So it can tell me whether current is being fed to the battery or being taken away from the battery. So what you'll see on an amp meter is it will have a little dial and it'll be 0. Let's just go 10, 20, 30, and let's just say this is minus, and then this would be plus 10, plus 20, plus 30. So as if we have the key turned off and we have all our lights on, this is going to point in that direction. But once we start the vehicle and it starts to charge, it's then going to point in this direction at however many amps that alternator is producing. The second one is a voltage regulator, or is a voltmeter, and these are on a dash. Now, a voltmeter is set up in parallel, and it has to have its own ground. And the third style is just an indicator light on the dash. So when I turn my key on, the indicator lamp will light up because it's getting its ground through the circuit. What happens when I start it is as this starts to charge, I get power being fed up here, and if I got power on both sides of a light bulb goes out. Now, if this resistor fails, what can happen is as you rev it up, the light will get brighter, and as you let off on the throttle, the light will get dimmer. You know that something's wrong with that indicator. Now, one of the other things I forgot to mention is on an amp meter, when we're installing an amp meter, on the back of the amp meter you'll see some things that say negative and positive. So if we hook it up backwards, it will read backwards. So make sure you hook the wires up in the right direction. Okay, that's it for alternators, and now we're going to go into alternator testing.